In this lecture, we will discuss numerical problems based on equilibrium constant and equilibria in various processes. As I have repeatedly emphasized on the significance of equilibrium constant, its importance in academics as well as in industry, and therefore, it becomes very important to see how to deal with different situations when it comes to optimization of the processes and deciding the conditions which are most suitable for getting a maximum yield. So, let us discuss a variety of numerical problems in this lecture. As an example, the first one is the data shown below. The data below show the temperature variation of the equilibrium constant of the reaction silver carbonate solid forming silver oxide plus carbon dioxide. Calculate the standard reaction enthalpy of the decomposition. Temperature in Kelvin is given and the value of equilibrium constant at these temperatures is also given. Let us carefully look at the information given. The given reaction is this decomposition reaction of silver carbonate, and we have the information on temperature dependence of equilibrium constant. We have been asked to calculate the standard reaction enthalpy. So, immediately we should think of some relation which connects the temperature dependence of equilibrium constant with the enthalpy, and this equation is the well known Hoff equation. Let us see what is Hoff equation. It is d log k by dt at constant pressure is equal to reaction enthalpy by RT square. And since we have been given information on the temperature dependence of equilibrium constant, and we have been given at least 4 temperatures. So, therefore, what I will do is I will write this equation in this form: d log k is equal to delta H naught by RT square Tt, and perform an integration. What I will have is log k is minus delta H naught by RT plus a constant. As we have discussed during the lecture, this equation we have discussed during the lecture. Now, what we have been given is the value of k at different temperature. So, what we will do is we will plot log k against 1 by t, and obviously, when you plot log k against 1 by t, minus delta H naught by R is the slope. One thing to be remembered while we are solving this type of question is that we have to know whether the reaction enthalpy depends upon temperature or not. Usually, when the temperature range is small, we safely assume that the reaction enthalpy is independent of temperature. Now, let us look at the equation that we derived over here. When I integrated this equation, I assumed here that delta H naught does not depend upon temperature. Now, let us go to the slide and recognize the significance, importance of this very important equation, Hoff equation. And as I just discussed, an integrated form of this Hoff equation can be written as log k is equal to minus delta H naught by T plus a constant. And we plot log k versus 1 by T to get delta H naught. As I just discussed, that if I plot log k versus 1 by T, there has to be R over here. So, the slope is going to be minus delta H R H naught by R. Please note down, there is R here in the denominator. And now you rearrange and substitute the value of R as 8.314 joules per Kelvin per mole. The overall value comes out to be plus 80 kilojoules per mole. The standard reaction enthalpy is coming out to be plus 80 kilojoules per mole. Let us comment on this plus. Plus means reaction is endothermic. If the reaction is endothermic, then according to Lee-Chatelier principle, if we increase the temperature, the value of equilibrium constant should also increase. And let us see whether the given data is in accordance with this. What we see here is when the temperature is changed from 350 to 500 Kelvin, the value of equilibrium constant increases from 3.98 into 10 raised to the power minus 4 to 1.48. So, this is in accordance with Lee-Chatelier principle. Since the K value is increasing with temperature, therefore, the reaction must be endothermic, and that is what we found out. Now, let us discuss another type of question. The question is, the standard Gibbs energy of formation of ammonia is minus 16.5 kilojoules per mole at 298 Kelvin. What is the reaction Gibbs energy when the partial pressure of nitrogen, hydrogen and ammonia treated as perfect gases are 3 bar, 1 bar and 4 bar respectively? What is the spontaneous direction of the reaction in this case? Once again, let us see what is the given information. The given information is that we are given the standard Gibbs energy of formation of ammonia, which is minus 16 kilojoules per mole. And we are also given the partial pressures of nitrogen, hydrogen and ammonia, and we have been asked that treat these gases as perfect gases. The partial pressures of nitrogen, hydrogen and ammonia are 3, 1 and 4 bar respectively. So, at this composition, we have to find out whether the reaction will be spontaneous or not. The spontaneous nature of a process will be predicted by the value of reaction Gibbs energy. If the reaction Gibbs energy or delta G at constant pressure and temperature turns out to be negative, then the reaction is spontaneous in the forward direction. In the context of given question, let us see what information do we have and how do we use it. Formation of ammonia can be written as half nitrogen gas plus 3 by 2 hydrogen gas forms NH3. For this reaction, I can write reaction Gibbs energy is equal to delta R G naught plus R T log Q, and Q will be equal to partial pressure of NH3 by P naught divided by partial pressure of nitrogen by P naught raised to the power 1 by 2 into partial pressure of hydrogen by P naught raised to the power 3 by 2. Since we are given the information that you treat these gases are ideal gases, therefore, I am using the pressures instead of fugacities. And now we have been given the partial pressures of ammonia, we have been given the partial pressure values of nitrogen and hydrogen, which we can substitute in this and find out whether delta Rg turns out to be positive or negative. Let us see what do we get. We go back to the slide. This is the given reaction, half nitrogen plus 3 by 2 hydrogen forming ammonia, and we have discussed that the Q, the value of Q is going to decide the value of delta Rg, because delta Rg naught at a given temperature is constant. That information is given. We are given that, we have been given that delta Rg naught. In fact, if you look at the given information is standard Gibbs energy of formation, and from the standard given energy given standard Gibbs energy of formation for this reaction, I can write delta R G naught is equal to free energy of formation of NH3 minus half free energy of formation of nitrogen minus 3 by 2 free energy of formation of hydrogen. Nitrogen and hydrogen being elements, their free energy of formation is 0. Therefore, the standard reaction Gibbs energy is equal to the Gibbs energy of formation of ammonia, and that information we can substitute in the slide over here. We defined Q as P by P naught of ammonia divided by P by P naught of nitrogen raised to the power 1 by 2 into P by P naught of hydrogen raised to power 3 by 2. You substitute the numbers, the given partial pressures are, for ammonia it is 4, for nitrogen it is 1, and for hydrogen for nitrogen it is 3, and for hydrogen it is 1. Once you substitute, you have the value of Q. Now, I will substitute the values of delta R G naught and Q into this equation. Delta G is equal to delta G naught plus R T log Q. The value comes out to be minus 14.4 kilojoules per mole. See, delta RG, reaction Gibbs energy is turning out to be negative. Reaction Gibbs energy is actually the slope of Gibbs energy against the extent of reaction. And if the slope is negative, that means the reaction in the forward direction is spontaneous. So, therefore, since we are talking about this particular reaction, then under the given conditions, the reaction will move towards the right hand side, that means more ammonia will be formed. And that is what is commented upon in the slide. Let us take a look at. Since delta R G is less than 0 at this composition, more ammonia will be formed. That means the reaction is spontaneous in the forward direction. Now, let us take a look at another question. Predict the effect of an increase in pressure on the composition of the ammonia synthesis at equilibrium. Assume perfect gas behavior. Synthesis of ammonia is very important industrially. Well known Haber's process is used. And in this question, we have been asked to predict what will be the effect on the composition of ammonia synthesis when the pressure is increased. So, in order to discuss the effect of pressure on the composition, first I will write the equation: nitrogen plus 3 hydrogen it forms 2NH3 gas. I can write 1 by 2, 3 by 2, whatever way you write, the actual final answer is going to be same. We have to find out what is the effect of pressure. As a first step, I will write an expression for K. K will be equal to partial pressure of ammonia by P naught raised to the power 2 divided by partial pressure of nitrogen by P naught into partial pressure of hydrogen by P naught raised to the power 3. And since we have been asked to find out the effect of increase in pressure, the total pressure, let us see which equation we can use which connects the partial pressure with the total pressure. And from elementary chemistry, we remember that Dalton's law of partial pressure can be used. That means partial pressure of any substance J will be equal to the mole fraction of J into the total pressure. That is from Dalton's law of partial pressure. We will use this information over here, and what we will have is, once you put, instead of P, you put mole fraction into the total pressure, I will have mole fraction of ammonia raised to the power 2 over mole fraction of nitrogen into mole fraction of hydrogen raised to the power 3, and pressure term is also there. So, it will be P by P naught raised to the power 2 minus 1 minus 3, that is 2 minus 4 is minus 2. can I write this ratio? I will write as Kx, that is a ratio of the mole fractions, into total pressure divided by P naught, which is 1 bar raised to the power minus 2. The effect of pressure on composition is given by Kx, because Kx is the ratio of mole fractions. Now, let us go to the slides. We took an example of this formation of ammonia from nitrogen and hydrogen, and we expressed equilibrium constant in terms of the ratio of the partial pressures converted into the product of mole fraction and the total pressure, and eventually came up with an expression that K is equal to Kx into P naught by P raised to the power 2. And actually here, if you look at what I showed here, is K is equal to Kx into P by P naught raised to the power minus 2, which is same as P naught by P raised to the power 2. Now, if we look at the slide, according to this equation, if I increase the pressure 10 times, since Kx does not depend on pressure, Kx is a constant at a given temperature, P will go on the other side and it goes as a square. So, 10 times increase in pressure will increase the value of Kx by 10 fold, that means it will become 100, 10 will become 100, sorry, it will become 100 fold. Since P goes, when you take P to the other side, it is a P square term. So, if you increase the pressure by 10 fold, Kx will increase by 100 fold. And Kx, you see, Kx is the ratio of the mole fractions of ammonia and the reactants. So, if Kx increases, that means the production of ammonia increases. And that is why you see the comment over here, the Haber synthesis of ammonia is run at high pressure in order to make use of this result. So, this example very clearly demonstrates the effect of pressure on the equilibrium composition. But let us derive a general expression which explains the effect, or which connects the effect of pressure on equilibrium constant, which is actually equilibrium constant is independent of pressure. What we need to talk about is Kx. K, let me write down now general thing. K is a product of activities. This is a general definition of K. And for perfect gases, I can write Pj by P naught raised to the power nu j, because we have discussed activity for a perfect gas can be replaced by P by P naught for ideal gas. And as I just discussed, let me, instead of partial pressure, let me write mole fraction of J into total pressure by P naught raised to the power nu j. Now, K I can write as, now when I expand this, I will expand separately for mole fraction and separately for P by P naught. It will be mole fraction of A raised to the power nu A into mole fraction of B raised to the power nu B into mole fraction of C raised to the power nu C, etc., into P by P naught raised to the power nu A, P by P naught raised to the power nu B, etc. Or I can write K is equal to Kx into P by P naught raised to the power delta nu, where delta nu is equal to summation j nu j, and this stoichiometric number is positive for products and negative for reactants. So, if we carefully examine this and we put positive sign for the product and negative sign with the stoichiometric number for the reactant, it actually is a ratio. It is actually is a ratio of the mole fractions, product of mole fractions of the products raised to the power by their appropriate stoichiometric number divided by the product of mole fractions of the reactant. So, this actually is Kx, K is equal to Kx into P by P naught raised to the power delta nu, and since if you combine all these P by P naught, these powers will be added. We have to put negative sign with the stoichiometric numbers for the reactants and positive sign for the stoichiometric number of the products, and overall sum is actually a difference between the number of moles of gaseous product and the number of moles of gaseous reactants. So, let us now go back to the slide. We want to talk about the relation between K and Kx, and I have just discussed this entire derivation and we came up with this expression K is equal to Kx into P by P naught delta nu, where delta nu is the difference in number of gaseous products and reactants. And this equation predicts the effect of pressure on equilibrium composition. Elementary textbooks describe the relationships between Kp and Kc. Kp is equal to Kc into RT raised to the power delta Ng. It works out well, but you know the Kp is expressed as the ratio of pressures, Kc is expressed as the ratio of concentrations, and this, although this equation works, but if you look at the units on each side, it runs into trouble. Therefore, this expression K is equal to Kx into P by P naught raised to the power delta Ng, or you can put delta nu is same as delta Ng, it does not run into any units problem. And this equation very clearly connects the Kx with the pressure. What will be the effect of pressure on the equilibrium composition? K remains constant with pressure, it is Kx which changes. So, I hope that these numerical problems have brought out the meaning of equilibrium constant and the effect of pressure on equilibrium constant in a more clearer manner. In the next tutorial, we will discuss the effect of temperature and few more problems to make an understanding of equilibrium and equilibrium constant still better. Thank you very much.